Welcome to Methods in Biostatistics. Have you ever wondered how scientists can confidently claim that smoking causes lung cancer or that a new drug effectively lowers blood pressure? They do not just guess based on visual patterns, they use precise mathematical tools. Today, we are going to explore one of the most important tools in a biostatistician's toolkit, the correlation coefficient. By the end of this lesson, you will understand exactly how to measure the hidden relationships in biological data. Let us start by building our intuition. Imagine you are observing two things that seem to change together, like the amount of sunlight a plant receives and how tall it grows. As the sunlight increases, the plant's height also tends to increase in a predictable way. This natural tendency for two different variables to move in harmony is what we call correlation. In biostatistics, we constantly look for these hidden relationships to understand how biological systems work. However, just noticing that two things move together is not enough for rigorous science. We need a precise way to measure exactly how strong that relationship is. Now that we understand what correlation is conceptually, let us define it formally. The correlation coefficient, often denoted by the letter R, is a statistical measure that calculates the strength and direction of the linear relationship between two quantitative variables. When we say linear, we mean that if you were to plot the data points on a graph, they would tend to form a straight line rather than a curve. This metric is the mathematical measuring tape we use to quantify exactly how closely two variables are linked together in a straight line pattern. Understanding this definition leads us to the scale of our measurement. The value of this coefficient always falls strictly between -1 and +1. A value of +1 indicates a perfect positive relationship, meaning as one variable goes up, the other goes up in perfect proportion. Conversely, a value of -1 indicates a perfect negative relationship, where one variable goes up exactly as the other goes down. If you calculate a value of 0, it means there is absolutely no linear relationship between the variables at all. So, why do we care so much about this specific number in biostatistics? Imagine a medical researcher trying to figure out if a new blood pressure medication is actually working across a large population. By calculating the correlation coefficient between the dosage given and the decrease in blood pressure, the researcher can mathematically prove if a relationship exists. Without this tool, we would just be guessing based on visual patterns, which can be highly misleading. It allows scientists to confidently link risk factors to diseases, thereby saving lives through objective, data-driven decisions. This brings us to the mathematical representation of our concept. The formula you see here calculates the Pearson correlation coefficient, denoted by R. Conceptually, the numerator measures how much the two variables vary together, while the denominator scales this by how much each variable varies on its own. Let us define the symbols. The variables x sub I and y sub I represent the individual data points, like the specific height and weight of one person. The symbols x bar and y bar represent the average or mean of all the x values and all the y values. If the variables move together strongly, the numerator grows large, pushing the final value closer to positive or -1. Now that we have seen the full formula, let us break it down conceptually, starting with the top half. The numerator calculates how much the two variables vary together. Think about what happens mathematically here. If a data point is above average in both x and y, multiplying those two positive deviations gives a positive number. Even if both are below average, multiplying two negative deviations also gives a positive number. However, if one is above average while the other is below, the product is negative. This sum is our first mathematical clue about the direction of the relationship. Moving to the bottom half of the equation, we have the denominator. This part calculates how much each variable varies entirely on its own, independent of the other. By squaring the deviations, summing them, and taking the square root, we create a scaling factor. This step is absolutely critical because it normalizes our data. Without this denominator, our result would depend heavily on the specific units we used, like milligrams or hours, making it impossible to compare different studies. Dividing by this spread leaves us with a pure, unitless number that represents only the relationship strength. With the formula broken down, let us see it in action with a concrete example. Suppose we want to find the correlation between hours studied, X, and test scores, Y, for 3 students. First, we calculate the averages, finding a mean of 2 hours studied and a mean score of 4. Next, we find the numerator by multiplying how far each student deviates from these averages, which sums to 4. Then, we calculate the denominator by squaring these deviations, summing them, and taking the square root, which also gives us 4. Finally, dividing the numerator by the denominator gives us exactly 1. This perfect positive 1 means that for every additional hour studied, the test score increases by a perfectly consistent amount. So we have calculated a correlation coefficient of exactly 1. But what does this actually mean in the real world? This result indicates a perfect positive linear relationship between hours studied and test scores in our small data set. Practically, this tells us that for every additional hour a student studies, their test score increases by a perfectly consistent and predictable amount. There is no randomness here. Because the value is exactly positive 1, this is the strongest possible positive relationship we can measure in biostatistics. Now that we understand a perfect positive relationship, let us look at a medical example. A biostatistician tests a drug designed to lower heart rate. We have dosage in milligrams as X and heart rate reduction in beats per minute as Y. We follow the exact same systematic approach. The average dosage is 4 milligrams, and the average reduction is 4 beats per minute. When we calculate the numerator, we get -4, because higher doses actually paired with lower reductions. The denominator calculation again gives us a scaling factor of 4. Dividing these gives a final correlation of -1. Physically, this perfect negative relationship means the drug is having the opposite of its intended effect at higher doses. We just calculated a correlation of -1 for our drug trial. Let us interpret this critical finding. This number indicates a perfect negative linear relationship between the drug dosage and the heart rate reduction. In practical medical terms, this means the drug is actually having the opposite of its intended effect at higher doses. As the dosage increases, the beneficial reduction in heart rate perfectly and consistently decreases. This is a critical finding for patient safety, and the math makes it undeniably clear. Having interpreted these numbers, let us visualize what they actually look like on a graph. Here, you are seeing 3 scatter plots that represent different correlation coefficients. On the left, we have a perfect positive correlation, where R equals +1. Notice how every single data point falls exactly on an upward-sloping straight line. In the middle, R equals 0, and the points are scattered completely randomly, showing no linear relationship at all. On the right, we see our drug dosage example, where R equals -1. The points form a perfect downward sloping line. These diagrams show how the mathematical formula perfectly captures the visual geometry of the data. We have covered a lot of ground today, so let us summarize the most important ideas. First, the correlation coefficient is an indispensable tool that quantifies the linear relationship between two variables. Second, remember that this single number always falls between -1 and +1, instantly telling us both the direction and strength of the interaction. Finally, while this metric provides the mathematical foundation for evidence-based conclusions, you must always remember the golden rule of statistics. Correlation simply measures a relationship. It does not prove that one variable causes the other to change. You now have the foundation to analyze biological data with mathematical confidence.